Welcome. So here we have to prove this integral, that integration from 0 to 2 pi of the function cos of 2 theta over 1 minus 2a cos theta plus a squared, you get 2 pi a squared over 1 minus a squared, and a squared is strictly less than 1. So to prove this problem, first we have to transform it into contour integral, where contour is the unit circle, and use residue calculus tool or use residue theorem to be able to find the solution. And our solution should converge this point because it's already given us 2 pi a squared over 1 minus a squared. So solution, we say let I be the given integral 0 to 2 pi cosine of 2 theta d theta divided by 1 minus 2a cos theta plus a squared. And you see, we can write this one as integral from 0 to 2 pi of cos 2 theta d theta over 1 minus a 2a into cos is the same as e raised power I theta plus e raised power minus I theta divided by 2, and then plus a squared. So which will give us integral from 0 to 2 pi of cos of 2 theta d theta 1 minus, so that these two cancels out. So we'll have a into e I theta plus e minus I theta plus a squared. Next step, open the brackets. So we'll have I is equals to 0 to 2 pi cosine of 2 theta d theta 1 minus a e raised power I theta minus a e raised power negative I theta plus a squared. Now you see the denominator is given by, so this denominator can be written as, so we have 1 minus a e raised power I theta minus a e raised power minus I theta plus a squared. You can write this one as 1 into 1 minus a e raised power I theta minus, so factor out a e raised power minus I theta. So then it dictates that this first term should be 1, and then minus a e raised power I theta. Since if you multiply this by this, negative is positive, so a times a is a squared, and then you have e raised power minus I theta times e raised power I theta. So law of indices tells us that minus I theta plus I theta is 0. So a squared e raised power 0, e raised power 0 is 1. So just give us a squared as we have in this position here. So then this will be 1 minus a e raised power I theta, and then another factor is 1 minus a e raised power minus I theta. So this denominator will be written as a product of these two factors. So let's write it. So we'll have our I integral to be integral from 0 to 2 pi of cosine of 2 theta d theta over 1 minus a e raised power I theta, and then 1 minus a e raised power minus I theta. Now, we can make this integral to be a gentle integral. So we say I would be the same as the real part of. Now, I write the integral 0 to 2 pi, and then cosine of 2 theta. Then I force an I sine 2 theta here so that I have the complex part. And then over 1 minus a e raised power I theta. And then 1 minus a e raised power minus I theta. This is d theta. And we say from Euler's identity, e raised power x is the same as cosine of x plus I sine x. So which means cos of 2 theta plus I sine of 2 theta is the same as e raised power 2 theta I. So therefore, I is the same as real part of the integral 0 to 2 pi of, now the numerator will be e raised power 2 theta I d theta over 1 minus a e raised power I theta 1 minus a e raised power minus I theta. So that's what we'll have. Now let z to be e raised power I theta. So which means when you work out z, dz will be, d theta will be dz over iz. It's not hard to see from here. And z raised power negative 1 equals to e raised power negative I theta, or really the same as 1 over z. So our I integral will be real part of. Now we change now, once we bring in the z, now we go to contour integration. So along say e raised power 2z. So when you say e raised power 2z, 2 theta I is the same as e raised power theta I squared, so the same as z squared. So therefore the numerator will be z squared over 1 minus a z, and then 1 minus a over z, this part, then dz over iz. Remember to specify that C is the unit circle. Good. So with this, we can have integral. Our I is a real part of this integral z squared. Now this iz multiplies every term here, so I can have multiply, so z, this is the same as 1 minus az times, so this is the same as z minus a over z. Then I can multiply this one by z. I put here the z, and then because I have an I here, I multiply by negative I, and then negative I, so that I times negative I is 1, and I'll have I to be the real part of this contour integral. I'll have negative z squared I dz. So this and this cancels out, so I'll have 1 minus az z minus a. So here, f of z will be this function. So it's negative z squared I over 1 minus az times z minus a. Now, once you have identified the f of z, you find now the poles of that f of z. So poles of f of z are taking the denominator and then equating to 0. When you solve this, you get z equals to 1 over a and z equals to a. Now, of these two poles, of these two poles, only z equals to a lies within the circle. The unit circle. Since a is less than 1, as we were told that a squared is less than 1. So which means the reciprocal of a should be greater than 1. So we only take those poles which are within the unit circle, so we don't have to take care of what is outside the circle. So residue at z equals to a will be given by limit as z approaches a of minus I z minus a times f of z, this by definition. So which means that this is the same as limit as z approaches a, z minus a, the function f of z we have minus z squared I divided by 1 minus az times z minus a. And so these two brackets cancels out. This reduces to limit z approaches a minus z squared I over 1 minus az. this should give the answer by direct substitution. So we'll have negative a squared I over 1 minus a times a, which is negative a squared I over 1 minus a squared. So by Cauchy's residue theorem, integral, contour integral around C of f of z dz is given by 2 pi I times sum of residues within the contour C. And because for our case, we only have one residue, because the other pole was outside the unit circle, this will give us 2 pi I times. So the answer there is negative a squared I over 1 minus a squared. And you see this will give us, so this I times I is I squared, which is -1, and -1 times this -1, +1, we just have 2 pi a squared over 1 minus a squared, which is purely real. And that was our interest, to find the real value of the integral. Hence, we have shown that the integral from 0 to 2 pi of the function cos of 2 theta divided by 1 minus 2a cos theta plus a squared is the same as 2 pi a squared over 1 minus a squared for a squared strictly less than 1. So that is how we have to prove that given problem. Thank you.